marcado onde está o registration, tem nada? afternoon. Let's start our afternoon session. The first speaker is going to be Tobias Frederico from Instituto Tecnológico de Aeronáutica. He's going to talk about light hadron structure and dynamics in Minkowski space.
Thank you, Arlene. So first of all, I would like to thank the organizers for the opportunity to show the work we've been developing now for about a decade on this direction. I will show some recent results we have been obtained, and I will focus on the pion. The pion already was mentioned in this morning as a key point understanding the mass of the nucleus. And the pion is really related to the Goldstone boson of the spontaneous chiral symmetry breaking that happens in QCD. And, but it's not at all trivial. I mean, we know that there are many things, quarks, gluons, distributing inside it. And what I will talk about, I mean, this is a structure, is a single state, and how do we look that with the purpose to go to deep inelastic or even to obtain other observables of the pion? We look there from the point of view of the light front, where the pion state has many four components. Here in particular, I put the valence plus, I mean, QQ bar plus glue and so on. And what is this wave function? It is defined on the null plane. Already been mentioned about the light from time. So this null plane is characterized by x plus equals 0. So this is a hyperplane that the distances are of the type of space-like, and therefore we can define a state on it. Okay, how we measure it? This was already mentioned. We assess the pion structure is one of the possibilities is through this Sullivan process, so we can get electromagnetic form factor, deep inelastic, parton distributions, and so on. No? And of course, we have to be a little careful that this pion is off-shell, but is very close to the region, to the physical region where the Sullivan process occurs, because it is very light. No? Okay, so the observables I will discuss for the pion, we know, I mean, this beautiful diagram that has everything is unified by the generalized transverse momentum distribution. And then I will look to the TMDs for the pion, and also the PDF and the form factor. So these are the observables that I will concentrate on it. And also one thing more I will talk about the 3D image. But what image? Is the Fourier transform of the valence wave function of the pion on the null plane, on the hyperplane x plus equals 0. So we have really, I mean, a wave function, we can look at the momentum distribution. So this is the image that I will talk about. Okay, so the model. So this is when we want to describe the pion in Minkowski space in continuum approach, we use the Bitzel-Peter equation. And what is the model we are adopting? We adopt one gluon exchange, no? And I mean, the elements in principle are dressed. Of course, this is a very simplified kernel. And you could ask why you do not put cross ladders and so on. Indeed, we made an investigation about the cross ladder. It's not so important. And when we have NC equal 3, no, even with NC equal 3. So what we have to have some ideas on this kind of model. What is the dressed quark propagator, the dressed gluon propagator, and also the dressed vertex. So these are the ingredients, and our idea or our approach is to solve this equation fully in Minkowski space without Wick rotation. And this was the technical challenge that we are faced. Okay, so the model parameters that we have to have, okay, the constituent quark mass, gluon mass. Of course, this is an approximate concept. No, and what is about the size of this vertex? Okay, so now we resort to calibrate this kind of model to lattice QCD. And this is just the gluon propagator in Landau gauge. And this is the gluon dressing function. And you see, this is p squared multiplied by the dressing function. And of course, if this dressing function do not go to a constant at q squared equals 0, so these are the lattice results. So this cannot go to 0. It will go to a constant. And from this slope, you can more or less have an idea or a scale for the gluon mass, about 500 MeV, that this is one of the inputs that we are going to use. The other input that is also plotted here is the quark propagator. We have of course, the wave function renormalization that in the infrared, you see, this is about 1 GeV or less. Of course, there is some structure here going to 0.7, as well as the mass that you have this calculation coming from 350 and then going to so this is a space-like momentum, of course, that you assess in the lattice. So from here, I mean, you think about a constituent mass with between 200 and 300 if you just think an average. Okay, so these are the first scales, and how to introduce the vertex. So this we rely to some work we have been done a couple of years ago with Bruno, Pacheco, no? And Orlando Oliveira, that we look to the Schwinger-Dyson equation, just looking in the following way. We know the dressing of the quark. We know the dressing of the gluon. So we could try to extract, of course, this is a U-defined problem, but you could try to assess some information on this vertex. And then we just look at this equation as an equation for the vertex. And we just take into account longitudinal components. Of course, this is the standard coupling, I mean the bare coupling, if you want. And of course, you have altogether 12 components, 12 form factors. And then what we did, we fitted some functions to the longitudinal form factors, just in a way that we could close this equation. Okay, this is a phenomenological approach, but what we wanted from that, to have some idea on the size of this form factor, or what is the scale. Okay, so this is what we got. I will not go, also Arlene has works on this direction that we based our work, no, in particular the Slanov-Taylor identity, Quargo scan. We used a lot of technical points, but the result is here. And this is, for us, is what is important. You see lambda 1. So this is the two independent momentum that we have. We are using, in the Euclidean space, we have two more independent momentum, and then we can put the angle between them 0. This is what we are plotting here. No? And then what we see, this is the asymptotic region when you go to large P and Q. And this should go to 1 in a very large momentum region. And what we see is a huge enhancement of lambda 1 that you see this is 25. Because this is what we expect. QCD should give you a lot of enhancement in the infrared region. And of course, the same we observe for the other form factors. But our model is simple. So we are going just to work with this form factor, or gamma mu coupling of the gluon, of this effective gluon to the quark. And what is the scale of this peak? It's about 300 MeV. No, if you look here, that is lambda QCD essentially. Okay, so this is the main, how I say, idea that we get from that. So we are calibrating the model. Of course, you could say, okay, this will give you a reasonable pion. let us see. Maybe it doesn't give, maybe yes, maybe no. Okay, so now we have numbers. So we solve it again. We go back to the bit-salpeter equation. We have here a constituent quark mass that we choose in this range. We need to do some fine tuning. We have the gluon propagation. This is Feynman gauge, although I talked about Landau gauge, but this was even more simple for the technical point of view. And we have a mass of about 500 MeV. No? And then the gluon, the quark gluon vertex, lambda 1, we use a form factor that has lambda about 300 MeV. So this is where we started with. Okay, now we solve this equation. Of course, we have the normalization. We have this coupling constant here. How do we get? We tune this coupling constant in such a way that we get the pion mass. Okay, and this model does not have absolute confinement, just have confinement in the sense of the bound state. No? Okay, so this is the model. How do we solve? So this was our main effort for almost a decade to have the solution of the bit-salpeter equation in Minkowski space. So we have we decompose, standard, the bit-salpeter amplitude in 4 invariants, and each of these invariants, so this is the Dirac structures. You see the standard gamma 5 and so on because of this pseudo-scalar nature. Phi 1, phi 2, phi 3, phi 4. These are scalars functions. These scalar functions, the technique we used was to represent with the Nakanishi integral representation. So this was, derived in the context of perturbation theory. And you may wonder that this does not work in the non-perturbative. We are going to solve a non-perturbative problem. Okay, so this is our starting point. So what we do, we use this representation, introduce in the bit-salpeter equation, but we do one simplification more, a technical simplification, that we project each of these 4 amplitudes on the null plane. So you could be surprised that you lose information, but not. No? So we project that, and then the integral equation we have, in this side I have those scalar amplitudes, and then I have 4 coupled equations. And what you see here, when you project onto the light front, essentially, you have the characteristic of a valence wave function. But the important point of this form is that this is a generalized Stieltjes transform. And this is mathematically well-defined with an inversion. So therefore, we could, in principle, just take out this denominator and solve this problem. But in the way we have now, we are using this form that was the form proposed in the works by Karmanov and Carbonell. But in principle, we could invert this exactly. Okay, and also, you say the life is simple, not yet, because when we project to the light front, those K minus integration, we are full with endpoint singularities. And then we are able to treat everything. No? The ones that are interested on this technicality can just look to our papers. Okay, so we solve this problem as an eigenvalue problem that we give the pion mass. So this kappa, essentially, I forget to write, but just give you is related to the mass of the pion and the mass of the quarks. And okay, you just give the pion mass, everything else. We have the gluon mass, the quark mass, and the form of the form factor. We solve it as a generalized eigenvalue problem. Okay, and from that, we can get, of course, we can do the normalization of the standard normalization of the bit-salpeter amplitude. Why I'm pointing to that? We can get the valence probability from that. And we can derive, I mean, for those amplitudes, this is just the way, the pion has two components, the anti-aligned spin component and the aligned one, no, that compose the valence light front wave function. And this, of course, is purely of relativistic nature, no? And then we can exactly compute, and for example, compute the decay constant, I will show, and the PDF for this guy. So after we play a little bit, I mean, with the parameters, so these are the parameterization we choose. So this is F pi, 130 MeV. So this is the one with square root of 2, okay? So some people just use the 93, but we use it without that. So we can compute F pi exactly. We normalize the bits of Peter amplitude. We can get the valence probability. And this was our preferred choice, okay? So with a constituent quark mass of 255, this is the binding. Remember, this is a bound state. This is the mass of the gluon that is about 600 MeV, and the parameter, the scaling parameter of the vertex function about 300 MeV. As we started, it was not far. Okay, very good. And then fixing the pion mass, we can get the coupling constant, and we can get the first thing, the valence probability. In this model, 70%. And then this is the first shock. What is the other 30%? Are in the gluons. Remember when I mentioned about what is the pion in the beginning? And the anti-parallel is 57%, and the parallel one, 13%, so it's small to compose 70%. Okay, so the first information we get, if I want to look to the quark PDF, besides the valence contribution, we have the contribution of the higher four components that are built in the model. Remember, this is a four-dimensional model, so all the retardation, so the gluon is dynamic, is a dynamical constituent. And this is just the distribution amplitude. We see here in red the anti-parallel. You see the endpoint of the distribution amplitude it decays faster than the anti-parallel because, of course, the anti-parallel is of relativistic nature. It should explore, I mean, shorter distance, and this will be related to the that is more broad, no? And this. And the same for the momentum distribution, we can see. No, this is just a transverse amplitude. And indeed, just as a curiosity, we can obtain those transverse amplitudes directly from Euclidean calculations. Okay, so this is going a little bit more for the valence TMD. So this is the parameterization we use it, and when we integrate over gamma, this gives you our PDF for the valence contribution, and we can see the exponent here that goes at the endpoints. Of course, the anti-parallel goes faster, I mean, to zero at the endpoints than the anti-parallel. So when we sum both, of course, is a kind of average. So we should have the two of them. Okay, so now the image. So this is really the image. What we are going to look is what is the wave function, the valence wave function on this hyperplane. So instead of the hyperplane t equals 0 that we are used to write down our momentum distribution, our densities, now we are going to look the density here. So we have the transverse variable, and we have a longitudinal variable that is x minus. And this was already, I mean, discussed not too long ago by Jerry Miller and Stan Brodsky, that this variable here we could use to see the image. But now the image is really the configuration space image the valence pion on this hyperplane. And of course, this we write everything in terms. This is also known as the now I forget Yoffie time. Okay, Yoffie time, but it's not a time; it's really a position here. And then, of course, you can look at this x dot p and write in this way, and you factorize. So this will be a dimensionless. This z tilde will be a dimensionless quantity. And this was the proposition to plot in this way. Okay, so how it looks like. So this is what we have. What we did, Fourier transform of the valence wave function in momentum space. We have the two components, the anti-parallel and the parallel. And then, of course, as we have a bound state, the wave function just goes exponentially to zero at large transverse distance. So we just factorize this factor, no? And there is other factors that you can take from the Fourier transform. And then we just look to this quantity. We multiply by b. B is the impact parameter, no? So it's bx squared plus by squared square root. So this is b. And of course, there is rotational invariance in the pion in the transverse plane. And this is what we see. So this is as a function of b and z. So of course, we have this structure, but remember this function. You may wonder that this is not going to zero because we factorize this exponential. And this is we taking a look on the dependence along z tilde here. And then we just, to simplify the plot, we just integrate on the impact parameter. And then, of course, we see a lot of oscillations because we have a compact variable, essentially. Okay, so now how it looks like. So this is the image of the valence component of the wave function, so of the pion wave function. So these are the two components, anti-aligned, aligned, and we multiply by b, you see this b, and this you have this whole, and this is the total. Of course, when we sum these two components, or these two components, that is the relative weight between the anti-aligned spin component and the aligned. Remember that this is about 50% and this is 10%. And this is the image we have. We see these different courses because of, of those oscillations. So this is the pion. This is really the 3D image of the pion valence wave function. No? Okay, so what else we can get? So far, we didn't compare it to data. So we use the depth parameters that I mentioned to you already for the pion and computed the form factor. And then this is start to be maybe more serious because we get, this is the electromagnetic form factor divided by the monopole. So this is the data we collected. And this black part, this black one, is the one that we used that give this f pi 130 MeV. And this is the data. The dashed one in black is just the valence component. And of course, at zero momentum, we have just how much of the charge or the normalization the valence component take, that is 70%. No? And then, of course, at some point, we know that the valence will be dominating, and but it's quite large momentum. Okay, this is another view of Q squared FQ, and then we plotted here. This blue dashed here is the asymptotic formula by Lepage and Brodsky. No? And this is the full form factor, and the dashed is exactly the one that comes from the valence contribution. And of course, at some point, this should match. And the Lepage-Brodsky asymptotic formula for the form factor relies on the dominance of the valence. Okay, thank you. Okay, so we see that to go to the asymptotic formula when the valence and the full form factor matches, we really need to go to quite large square momentum transfer. So this is the message. Okay, so now I just want to call your attention as we can have the valence contribution to the radius, to the pion charge radius. We have the full pion charge radius that we computed. So we can have an insight what is the charge distributed in the higher Fock components of the pion. And this is what we get. From this calculation, we have the pion radius matching quite well the experimental, this experimental value, that is the total. And the valence, the radius, the charge radius of the valence is 0.71. And therefore, we can compose the full pion radius, take into account the valence probability and the probability of the higher Fock components. And we see, as we could imagine, that the non-valence or the higher Fock states that has higher virtualities, they should be more compact. And this is indeed what we see. This is just a halo. So the valence formed like a halo. And then inside, we have the contribution of the higher Fock components. Okay, so now we can go to the Parton distribution. And this is the total, I put the formula, but this is the standard. So for that model, this is the Parton, the longitudinal momentum distribution of the quark, and this is the valence. This is normalized to 1, and this is 207. So we can see, so the difference, again, from where it comes, from the higher Fock components. No? And the endpoint behavior is about 1.4 in our model. Okay, so now we have to set up a scale to this model, what we did. So we fitted the lattice QCD at 2 GeV, the average, the first Melling moment, no? And this is what we did. And how we did? We used the GLAP equation in lowest order using the idea of effective charge. Effective charge saturates at 0 momentum to pi. Alpha saturates to pi. And this is, we just follow, what is in this paper by Q et al. So we did first leading order evolution with this effective charge. So it saturates. And this is what we got. We fitted, this momentum, and this is the scale of this pion. And then, of course, we can compute for 5 GeV. This is from lattice, and this is not so bad, what we see here. Okay, so this is what we got. This is the lattice results. This band, gray band. So this is our calculations for psi, u psi. And these are other calculations that are, difference between the approaches from Dyson-Schwinger equation. So this is by Bednar. This dashed line is from Cui et al. This is the group of Craig Roberts. And there is also BLFQ. So basis like front quantization, that is the group led by James Berry. And then we see that we have this exponent here is about 1. So this is at 5 GeV momentum. Okay, so now this is the data that exists. That is the one from the original E615 data extraction, and this is with log by this Eichert-Schaefer log. And this seems, to agree with that. And this is the valence contribution, okay? Okay, so now we go a little bit less. Before, what we did, we make an average between the quark and anti-quark contribution. So we have that the PDF was symmetric around psi 1/2. So now we pin down one quark. And what we found is that this is the black curve. We see a dislocation towards a little bit small psi. This is the valence, and this is the valence symmetric because of charge conjugation. The QQ bar, in our case, has the same mass. And this is the previous one. And then we see a little dislocation. Why? No? And if we compute from this guy, the first Melling moment, if it is symmetric, it's 0.5. But in this case, it's a little bit smaller. Why that? It's because of the gluons we have, the dynamical gluons we have, the higher Fock component. And this just to remember you that we have in this pion QQ bar and so on. Our model, I mean, this ladder model, you can show this is the kind of Fock components you can have. So QQ bar gluon, QQ bar two gluons. Of course, those quarks are constituent quarks, are not mere quarks. So once you address these degrees of freedom, no, these are the ones that are in this expansion. Okay, so just to have a very naive view on why this comes out. So this is, I mean, the bit salpeter amplitude. So this is the process for breaking up the pion. We have an anti-quark and the quark. The photon is here. When we look from the point of view of the light front, I mean, at some time, this is these lines. We have here the valence contribution, but I could have gluons being sent, more gluons, and so on. No? And of course, when you send those gluons naively, you have a little bit less momentum that this quark had. No? And this is the idea. Okay, so this will be this gluon radiation in the initial state interaction. But this is buried in the Minkowski space calculation. So now what we do? So this is the formula, the standard formula for the parton distribution as a function of the momentum fraction. We have here n equal to infinity. This sum means the valence contribution, n equal 3, that will be this guy, and so on. And of course, when we think about that, this is our the density. This is what we are looking to this momentum distribution. When we take the quark from a higher Fock component, he has less than 1/2 momentum because he has to share its momentum with the other degrees of freedom. And then if we play a little bit with the sum rule for the first moment, that remember we got 0.471, we know the valence, we know the beyond the valence. So these are the contributions from the higher Fock components. We can extract the gluon first moment. We just play just using the sum rule. And then what we find for this model is that indeed gluon carries at the pion scale, at Laue scale, something like 6% of the longitudinal momentum of the pion. Okay, we look at also to the transverse momentum distribution. We could only compare with some work by Cedric, and I mean, there is not yet, as far as I know, data for that. We computed two of them, the scalar and the transverse one, so EQ and F perp. So gamma, just to point out, is K perp square. No, we are always putting gamma, but it's just K perp square. Okay, and this is what we get. No, I mean, we computed this side, no, with all that. And this was proposed by Cedric, Barbara, and Schweitzer, that to separate the higher contributions, and the valence one is here. And this is the valence, in this case for EQ, and this is the full, it's quite different. And the same here for the transverse. So, okay, so we can compare only with the valence and other works. I mean, as far as I remember, they have computed also from the valence wave function, and is similar to what we show here. Okay, so now, what is the next? How much time I have? 5 minutes, very good. What's next? Okay, we put a constituent mass fixed, but we know, as I showed, and not only from the lattice results, but many people have already shown in the past by continuous methods that the quark gets some self-energy, and this is the reason for chiral symmetry breaking. This is very strong, and this also gives the mass to the nucleus, we know of that. So we have, of course, this model of the pion we have is very poor in this side. So we have started to think about how to improve. One of the things, and we must remind that we are working in Minkowski space. So if we want to introduce a running mass for the quark, we should have a formula that we are able to analytically extend to the Minkowski space, so to the space-like momentum region and timeline. And then we just assumed for the running mass, so we put the wave function renormalization 1, is really a very simple model, and the running mass that you see the I epsilon. So we do not lose any causality on that. And in space-like momentum, it just fits. This is some old lattice data. Okay, and then what we do now? Okay, we have to solve again the bits of Peter. No, the amplitude have 4 terms. But one thing, we started to play the following game. Using the axial word identities, we know that in the limit where the bare mass of the quark is 0, the vertex, the pion vertex in the bits of Peter amplitude is just given by, in this case, by the mass, because we are putting the wave function renormalization 1. So we can build a model just using lattice data, not else. And this is indeed what we did. First, I just want to show, this is something maybe technically is interesting. These are the Nakanishi weight functions. So how they depend for that model with Z. So this is G1, G2, and here I put a G3 and G4, and the dependence on gamma. So they are very non-trivial, even for this trivial model. No? Just to remind, and this is, of course, what we have by solving the bits of Peter amplitude is a pattern even more complex than that. Okay, so these are the results for the valence distribution. So the dashed one was our model with fixed mass, and this is from this model with running mass that, okay, the probability in this model is about 60% for the up-down, and then 10% for the anti-parallel, 70%. So this is, we can compare with our calculations of the fixed mass. So it's not so bad, indeed. Okay, now there is more work. I just want to show that this model, besides in the original model, we look at to the pion form factor, and people have looked in also to the pi gamma form factor, so the pi naught producing a gamma, and also to the distribution amplitude. And MMF is this model that was our original proposal, and you see this is the asymptotic limit, and this you see here, the dashed one was a proposal by this group of several years ago. So we see some oscillation here. And these are the pion form factor. You see that this original model was not so bad. It's this point. This is Babar data and so on. So it's really amazing with how little you can do and how much you can get. Okay, so the next challenge was to introduce the running quark propagator in those bits of Peter equation. What we did, we fitted, again, we repeated the running mass to some new data, more recent one. So this is from 2019. Our original paper was from 2017. And this is what we have. The infrared mass is about 344 GeV. We changed a little bit the parameters. And this is the continuous line is the fit by this simple formula. Dashed line is from lattice, this work. Okay, we can play, of course. This model is very interesting because it gives you 3 poles. I just want to call your attention. Real poles, so time-like poles, not complex poles. And we have 3 poles, the lowest one with mass 0.47, 0.57, and 1 GeV. And these are the residues. You see, it's very far from 1. Okay. And then what we got, this is our results, okay? And for the moment, we have a very heavy pile, you see, because this is not easy numerically. We have a pile mass of 650 and 500. And this we compare, we use the same model with the same gluon mass, with the same vertex parameter for the quark-glue interaction. And what happens when we put the running mass? So I mean, the fixed mass case is calibrated with the infrared mass, 340. So you see the difference between the dashed to the continuous. So this is constant mass, running mass, and this is for, I mean, this heavy pile, but the trend is more or less the same. When we decrease, we see this kind of behavior. Or you have a shrink or a broadening. And the same we see in the transverse direction of, and this is for the valence contribution. For the moment, we are just computing. Okay, I will not tell about our efforts also of solving the Dyson-Schwinger equation on Minkowski space, because this is an essential ingredient to go beyond a simple model and go to my conclusions. So we have in progress this work on the Witzel-Peter equation to solve for the pile with the quark self-energy. For the moment, this simple model, and we worked out also the solution of the Schwinger-Dyson equation also for a simple model in Minkowski space, but we went up to the region where we have spontaneous chiral symmetry breaking. And okay, I showed the results for pile form factors, T-even, TMDs, and this, of course, is our future. But before I finish, I want to advertise that I think this community is also very interested, that will happen the LightCon 23 in Rio de Janeiro in the Brazilian Center for Physics Research, where Feynman was. And the page is already on. If you want to have more information, I'm still getting the hotels and so on. And it will open the registration on 15th of May. So the ones that are interested, please visit the page. I will soon also advertise in EI, in the users group. Okay, thank you very much.
Questions, comments? Okay, I think the first one was there. I'm going to try to take the microphone to the question.
Okay. Okay, so a very simple question to be asked. What's the main difference between your model about this running quark mass and the one used by Craig Roberts?
Oh, okay. The main difference, there are a couple of them, no? First, the dynamics. They have this Maristan kernel, an improved one, that he has confinement. We don't have. We have a bound state in the sense of quantum mechanics, but relativistic quantum mechanics. So we can, in principle, we are not generating a spectrum of the pion. But as the pion is strongly bound, is deep in the interaction, maybe this explains why good results we got. And the other difference is a technical difference, and this is what we invested 10 years, is to solve those equations in Minkowski space. Because it's not easy to come from Euclidean space to Minkowski space, because you need to do all analytic continuation. There are people like Gernot-Eichmann that is doing that is also not easy. And the group of Craig and Ian Chloe, they have other methods of expanding in many moments and so on. So our main contribution is to try first, not to solve everything, but get ingredients from lattice and compute everything in Minkowski space. This is important, I believe, to understand the endpoint behavior. That is a very huge battle of the PDF, no, the endpoint behaviors. And okay, this is the main, I would say, the main points, but in philosophy is completely aligned with Craig, with Ian Chloe, and Gernot-Eichmann. There are other groups that are, I think Adnan and Arleni, but they work in Euclidean space, yeah. Okay, Pache.
Thanks for the nice talk overview. And why you need to go to your time to project the wave function?
Yeah, because the idea to see that, I mean, that funny donuts, I mean, the format, because, I mean, in the new plane, you have exactly, you can define the wave function in principle. There are also discussions on that. But suppose you can define, instead of t equals 0, that we have, I mean, quantum mechanical wave function, we think about this new plane. But now we have the Fock decomposition. Of course, the first term, according to these models, the major contribution comes from the valence, 70%. And this is what I plot. It is really, how do you see the square modulus of the wave function on this plane? So we made the Fourier transform. So this is maybe is more intuitive, I mean, to this image. This is really the image. It's like you take the deuteron and you plot the density distribution. It's exactly the same, but this is in x plus equals 0. So this is, I mean, is get you some visualization. How good this is, I mean, to learn something more, okay, it's open to debate. Because all those PDF, TMDs, and so on, indeed, in principle, are observables related to the light, I mean, to your light front wave function. No, I mean, in this picture.
Yeah.
Oh, okay.
Yeah. Thanks for the talk. A question and a request. So start with the request. You have already given a long list of things that you want to do.
Yeah.
Could you also calculate the gravitational form factors?
We are discussing this today.
Great.
I was
Great.
with Saume discussing about that. This is one next point. But what we need now, I mean, there was a big effort by Emmanuel Idrefors that maybe you met. He was a year in Saclay, no? And we need a lot of computational effort. This is one point. The other point, we need to compute any of these observables, the PDF, we have the integrations over those analytic structures are done, analytically. And we have the endpoint singularities to treat, you know very well. And this is, okay, we know everything, but this is quite an effort also from the theoretical point of view. At this moment, we have one student, Abigail, doing at least the solution with running mass. But we intend, I think it's very interesting to see the pressure, because as we have the bit salpeter amplitude, we can go beyond this skewness 0. No? So we could get essentially the gravitational form. But we need to formulate, I mean, in the general way, in such a way that we get the valence will not, I mean, because you need the pair. So you need higher, the overlap with higher Fock component. So we could eventually even see this decomposition. But this is in the plan, and we would like to do that, but we really need help. Maybe another, I'm applying now for a postdoc and to help on that.
Really quick question then. In your result, do you see any clear signature of the fact that the pion is a pseudo Goldstone boson?
The signature, because we don't solve at this moment, I mean, there are many things we have done. The works we have done on the solution of the bit-salpeter equation, the pion mass is given. So in principle, if you solve the Schwinger-Dyson equation together with the bit-salpeter, you have the mechanism built in of the dynamic chiral symmetry breaking. Now, the simple model we did with a student and João Pacheco, what we thought, okay, lattice give us the running, I mean, quark propagator. Now, the axial Ward-Takahashi identity in the limit where the current quark mass is 0, say that the vertex of the pion is just the B, the scalar form factor. And this we tested. I showed that. But this is, we just use it, I mean, those inputs. So if you want to say, if we see those observables, we could even use that to compute the gravitational form factor because we have it covariantly. We have not done that. Maybe it's a good suggestion. We could see, indeed, through this simple model, the effect of the chiral symmetry breaking because I mean, you define everything with the self-energy, at least in this limit, if you think that the current quark mass is not important. Otherwise, you have the other terms in the vertex. No? But it seems that we are seeing, if you want, with the simple model, yes. Pacheco, is better that you talk in the, yeah.
You have only non-valence components. This happening, it is model more sophisticated.
You say this model with the analytic quark mass, of course, we can see the gluons there. We could make the same trick we did for the bit-salpeter calculation and see what is the gluon contribution for that. I mean, but should be an effective gluon in some way because everything, but there is one important problem here, is how to define, I mean, these degrees of freedom, because there is, I always am worried about Haag's theorem that says that your Hilbert space of the free Hamiltonian is not the same of the interacting Hamiltonian. And this is what we are doing. We are using dressed degrees of freedom. So to answer your question, we could see maybe some shift. We could compute exactly in the same way what is the gluon momentum fraction in this guy, yeah, at the scale. Okay.
So let's thank again Tobias for
Thank
talk.
you.
The next speaker is going to be Captain Raya. Everything is there? Yeah? You changed it? Who changed the things? Do you know? You changed? Yeah. I'm going to tell you when you
I don't know.
5 minutes, I give you.
Okay, but can you hear me?
Yeah, okay. Okay, 5 minutes.
Very well, thank you. So, thank you very much for having me here and for this opportunity to present the culmination of this effort that we started in Huelva some time ago. I don't know, could we put it full screen mode? I don't know. Okay. Yeah, so basically what I am trying to tell you today is how to combine the information on the pion electromagnetic form factor and distribution function, the empirical, the experimental information, in order to build the generalized pattern distribution. But first, let me briefly recall what we all know about QCD. So this is characterized by two emergent phenomena. One is confinement. that basically tell us that the observable degrees of freedom are hadrons and not the quarks and gluon, the fundamental degrees of freedom. And the other one is the dynamical generation of mass that actually yields to the emergence of hadron masses. And the typical example, of course, is the proton mass, the most abundant and stable hadron in nature, in which only about 1% of its mass is attributed to the Higgs mechanism alone. The overwhelming rest comes from the complicated interactions from QCD and interplay with the Higgs, some interplay with the Higgs. Of course, one would like to understand the emergent phenomena in terms of fundamental degrees of freedom. For instance, it is said that by studying the analytical properties of green functions, one can get some light about the confinement properties. And focusing, for instance, on the quark propagator and the mass function, one can really see how the current quark masses are enhanced non-perturbatively by the effect of dynamical chiral symmetry breaking, which is particularly notorious in the light sector. From a couple MeVs, we arrive at a couple hundred MeVs, and even starting with the chiral limit, we basically generate mass from nothing. In the gauge sector, the non-abelian nature of QCD triggers the Schwinger mechanism in such a way that also the gluon develops some sort of running mass. So maybe Christina will discuss about this, I don't know. And of course, confinement and the emergence of hadron masses are tightly connected with the coupling, the running coupling in QCD. And this picture here is the process-independent effective charge that basically contains our modern understanding of the subject. Let's say the well-known ultraviolet fall-off, but followed by the enhancement and saturation in the infrared, with the smooth connection between both the ultraviolet and infrared domains. This, of course, will have implications on the formation of hadrons and the structural properties. Why focusing on the pion? Well, we just listened a really nice talk about why the pion is important. It's simple, it's light, it's the archetype of nuclear exchange forces, but it is also a Goldstone boson. So its mere existence is tightly connected with the underlying mechanism of mass generation in the standard model. And interestingly enough, as opposed to the proton, in the absence of Higgs mass generation, the pion will be massless. So that say, the experimental access to the pion is often given by electromagnetic proofs. For instance, from exclusive processes, we get the electromagnetic form factor, and on another kind of experiments or setups, we can get the valence quark distribution functions. Form factor and distribution functions are connected through a more general object dubbed GPD. The first of them as the zeroth moment of the GPD, and the second as the forward limit, in which the momentum transfer is turned to zero. It is, of course, challenging from the experimental point of view to get the GPD, but it is also the case from the theoretical point of view, because this object here is subject to a number of mathematical and physical constraints. So we will try to, from these simpler objects, build this more general distribution. So question, from the one-dimensional distributions, can we obtain the GPD? Today, I will try to give you a partial answer, and it works on the two premises. The first has to do with the effective charge and the all orders evolution, and it is like this. There exists at least one effective charge, such that when we solve our de Graaff equations, we will get a scheme that it is all orders exact. So in this way, given the fact that the experiment is given at some energy scale at which we have disentangled the valence, C, and gluon contributions, we can connect with the low energy scales at which we have just some components. In particular, we deal with the so-called hadronic scale, at which all properties are contained within the fully dressed valence quarks. In particular, all momentum is contained within the fully dressed valence quarks. So using this premise, we can connect the parton picture with the quasi-particle picture, one way or the other. The second premise is that a factorized representation of the electron wave function, namely that we can split the K-perp and X dependence, is a sensible approximation for the pion. Why we care about this? Because at least in the glab kinematic domain, using the overlap representation of the light from wave function, we can get the GPT. And as we shall see later on, a factorized light from wave function enables us to write down the GPT in a very convenient manner. So I will try to show you why we find sensible approximation for the pion light from wave function. So just a couple of words about light from wave functions. With this, you can get plenty of information about the structural properties of the hadrons, because you can get distribution amplitudes. We will have a talk tomorrow. We can get, as I said, the generalized parton distributions, and from there, the moments give you the gravitational and electromagnetic form factors, for instance, and the distribution functions. We can start from a more, let's say, a covariant framework, Dyson-Schwinger equations, whatever, you continuum Schwinger methods, and starting from the beta-salpeter wave function, as we have seen in the previous talk. But in our case, since we often deal with the Euclidean formulation, we start with the beta-salpeter wave function and project onto the light front. And this beta-salpeter wave function could come either from the solutions of the Dyson-Schwinger and beta-salpeter equations, or be constructed in a sensible manner, as will be discussed by Professor Bashir later in this workshop. So, but the thing here, and I'm not really focusing on light from wave functions and perturbation theory integral representations. I just want to show you some particular models that motivates us to use a factorized representation for the pion. Well, I will use in general just to sketch the flavor asymmetry, the kaon, for example. Let's take the beta-salpeter wave function of the kaon. Of course, we need a Dirac structure characterizing the pseudo-scalar nature of this method. It will be written down in terms of three denominators, the one coming from the quark, the anti-quark, and the beta-salpeter amplitude, and of course, the spectral weight. In this case, it is a very simple jet practical model. So after a series of algebraic steps, namely Feynman parametrization, change of variables, and also appealing to the uniqueness of Mellin moments, we can relate the light from wave function with the spectral weight, and then compute PDA or PDF. But it also works the other way around. We can use these objects to inform the spectral weight. In this particular case, we have this complicated expression for the light from wave function, an integration of the Feynman parameters and the Nakanishi weight. This is not the point of this slide. The point of this slide is that in the denominator here, I have the following. I have the quark mass, the anti-quark mass difference, this mass scale lambda, and the meson mass. And from here, we already see that in the chiral limit, this goes to 0, this goes to 0, and setting the mass scale to be the quark mass, we get rid of this integral, and we arrive at a very simple expression for the light from wave function. And actually, this expression is completely factorized. I can write this down in terms of the PDA or the PDF, because in the chiral limit, for this particular Nakanishi representation, the square of the PDA is the PDF. This, of course, defined at the hadronic scale. So it will be a sensible representation so long as we are dealing, or as long as we are near the chiral limit. And it is characterized by a single parameter, just the constituent mass. And sensible value for the constituent mass gives you the charge radius, or also the other way around. We can work out with a more general perturbation theory integral representation that includes some function lambda rather than just a mass scale. This particular choice helps us rid of all integrals concerning the Feynman parametrization and arrive at this close relation between the light from wave function and the PDA. But the important point here is that once again, this object here tells us that the flavor asymmetry and the meson mass encodes the breaking of the factorization. So once again, it will be, from this experience, a good idea to have it for the pion. So coming back to the point, to my actual point, because I am not focusing on light from wave functions, but on the GPD, the overlap representation let us write the GPD in the lab kinematic domain. It is restricted to this domain. Nevertheless, there are some fancy, let's say, very sophisticated numerical methods to extend it to the ERBL domain. So we don't really care about this at the present time. And within a factorized representation, I can write down the GPD as follows in terms of the PDF and this profile function phi that depends on this variable set. And this variable is nothing but the combination of the kinematical variables of the GPD. So I have reduced the complexity of having 3 kinematical variables to having just one times the PDF. And at this point, I want to stress that I will no longer care about light from wave function. I don't care where I get it, how to compute it. I just care about the fact that it is completely factorized. So I can write down the GPD as follows. What comes next? Well, I told you I want to combine the information of the valence quark PDF, but the valence quark PDF is not given at the hadronic scale, of course, because the interpretation of PDFs requires it to be above certain energies. So this is where the experiment happens, and this is where I can do my calculations. So in particular, I am dealing at the hadronic scale. As I said before, at this scale, everything is contained within the fully dressed valence quarks. And if I assume isospin symmetry inside the pion, that means that I have a 50-50 share of the total momentum. And furthermore, that I will have a symmetric distribution. Good. Here's a family of symmetric distributions of the hadronic scale. This one, the contact interaction result. The red one, it is like some sort of Parton-like profile because I am just keeping this coefficient that I expect from Parton models. And the blue one over here is the result from this group. So another thing that I can define at this hadronic scale for a symmetric PDF are the so-called physical boundaries. First, I will understand the contact interaction result as one of the boundaries because this is the case where the quarks don't talk to each other. They don't know nothing about each other. So every configuration is possible. It gives you these moments. And the other case is when I have infinitely heavy quarks. In that case, the distributions become increasingly narrower. The same happens with the PDA, as we will see. So the distribution becomes a delta function centered at x equal 1/2. And in that case, I get these moments for the PDF. So I will understand in the subsequent this as the physical boundaries. So with that in mind, let us go back to the experimental PDFs. Well, in order to get the PDF from experiment, this is a quite sensitive issue because we need to be careful about how to interpret this object in terms of cross sections. And this is some sort of debate, and this is some sort of very active issue currently. So I will do this exercise for a collection of different interpretations of the experimental data in order to see what happens when I choose one or another result. So what we do typically in theory is that we start with our model defined at some low energy scale. Through evolution, I get to compare with the experiment and with the lattice. And through the all-ordered scheme that I am about to define now, we will see that we can go either way. So this is a very important point in my construction of the GPD because I want to take the experimental or lattice PDF and take it back to the hadronic scale. So let's discuss about evolution. The equation here resembles the leading order, the Clap evolution equation. But I want it to be not a leading order approximation, but an exact equation. This requires to have this coupling, not the leading order coupling, but an effective coupling. So I can always do that, but I need to define it in some way. The process-independent effective charge I showed you at the beginning of the presentation is an excellent candidate because, as it was said before, it saturates in the infrared. So we can evolve both ways, and we can go deeper and deeper in the low energy scales. But very interestingly, if we don't use this equation, but if we perform the evolution in Mellin space, we can actually get this very nice relation. The moments at some scale are of course connected with the moments at the hadronic scale and the effective charge. But if I further work out the math, I can connect the moments at some scale with this ratio of momentum fractions. So this implicitly contains the information of the effective charge, but it is no longer there. The only thing I care about are the momentum fractions. So there is no need to know the details of the effective charge. I don't need to invent some effective charge. Just assuming its existence is sufficient to perform the evolution. And furthermore, knowing that at the hadronic scale, all the momentum is contained within the valence quarks, and in particular, assuming the isospin symmetry in the case of the pion, I can get a very nice relation for the moments of the valence distribution function. This is the first implication. The second implication is that from the valence, I can build up the C and the gluon with these very nice expressions from which the asymptotic limits become evident, and of course the momentum sum rule. A third implication of symmetric PDFs is the recurrence relation. In fact, with a symmetric PDF, I can write down the odd moments in terms of the previous even moments. So not all moments are linearly independent. So I get this recurrence relation. And just some exercise, these are the moments from some lattice collaboration. And using the even moments from this lattice collaboration, I predict this with this nice agreement, this also nice agreement, but I can give you even another one. So recurrence relation will be also important in the subsequent. So coming to the main part of the talk, let's do reverse engineering to the data. So we have different interpretations of the pion PDF experimental data. The original, I shared all on this analysis from this reference. I don't really care about the details. I will parameterize it in some way and find the best fit. After I find the best fit, I will generate randomly new fits around this one. And using a chi-square criteria, I will accept or reject this particular representation. If accepted, I use the evolution from moments to get a distribution at the hadronic scale. So I do this exercise, for instance, with the iChair et al. PDF. At the experimental scale, I get this band, this blue band over here. These are the moments with some deviations I get. So the produced moments are indeed compatible with a symmetric PDF at the hadronic scale, and not similar at all to the moments obtaining the contact interaction. That means I expect vanishing endpoints at the hadronic scale. So since everything is making sense, I reconstruct using this very simple functional form. Why? Because I only require one single parameter to get the broadness of the distribution, and also contains the Parton-like profile in some specific limit when this goes to infinity. Nice. I can do the same with lattice moments. I take the moments from different collaborations and keep those that verify the recurrence relation and also fall within the physical bounds, which are this. And if I use these lattice inputs, I get this nice band over there. So most of the replicas I get are dilated, good, but some of them are near or even containing the Parton-like profile. So we hope that in the future we can narrow this lattice band. So this is the PDF. This is a one-dimensional distribution. How to get the GPD? Well, I will need the information on the form factor. And this comes again, the factorization. Let us recall what is happening. We have a factorized like from wave function. I don't know where I get it. I just want it to be factorized, such that the GPD is written like this: the PDF and this profile function that depends only on this variable in terms of the kinematical variables of the GPD. Good. I will use different sets of PDFs and get this part, and I will use the empirical information on the form factor and this particular representation for phi. Nothing special about this representation. It just happens to be with only 3 parameters that can be reduced to 2 parameters if I somehow fixed a range for the pion charge radius. So the exercise is as follows. I take some PDF data set, generate a replica, and accept it or not. If accepted, I evolve back to the hadronic scale and give a representation for this particular replica. I will store the value of rho and the probability of acceptance. Good, I have a PDF. Second, since the form factor is this convolution of the PDF and the profile function phi, well, I use the previously accepted PDF. I generate random values for these parameters. And again, employing a chi-square criteria, I compute the probability of accepting this particular phi given this particular PDF. And finally, the GPD is accepted with this conditional probability. And repeat until I get many, many chords. So what happens when I perform this algorithm? Well, here is the Eicher et al. Case in blue as compared with the lattice one in gray. And here is this MF resumation in yellow, again, as compared with the lattice one. And interestingly enough, the dashed line corresponds to the chiral limit PTIR model that was put forward like 2 years ago, long before this data-driven approach. This is the front face of the GPD, namely the PDF. We see the lattice contains both Eicher et al. and MF resumation, nothing special from here. Also nothing special in the case of the form factors because the form factors were used as benchmarks to build up this object over there. The only thing, again, to highlight is that the lattice is containing basically the other results. Here is what is new, the gravitational form factor. In the Glab kinematic domain, it is already accessible, the gravitational form factor θ2. θ2 is associated with the mass distribution. θ1 is beyond the scope of the overlap because it requires the knowledge of the ERBL region. But for the time being, θ2 is sufficient. Here, I am comparing our result for θ2, Eicher et al. Case, MF resumation here. And you see that the comparison with the pion form factor tells us that the gravitational form factor is harder than the electromagnetic form factor. And this curve here, the solid curve here, is an ongoing Dyson-Schwinger equation computation with momentum-dependent interactions and symmetry-preserving kernels and vertices. So hopefully we will get this published soon. From here, we also learn the following. The charge radius, the mass radius is about these quantities in Fermi, producing this ratio for the mass and charge, about 0.8, so 20% difference between the mass and charge ratio. So the charge spans over a larger domain than the mass. But this is not necessarily an accident. Actually, from the factorized models, we get this expression for the GPD again. And in this case, we can relate the derivatives of this function phi with the derivatives of the form factor. And the proportionality constants are moments of the PDF. This is quite interesting because if I focus on the lowest order moments, then I get this really nice relation between the mass radius and the charge radius. So mass and charge radius are completely determined by the moments of the PDF. This ratio is completely determined by the moments of the PDF and not at all by the running of with delta square. So this gives us about this number. So not an accident. Well, in the lab kinematic domain, we can also compute the impact parameter space GPDs. Here we have the Eicher et al. Case, the MF approximation case as compared with lattice. In this case, the MF case, it produces the more peaked distributions because it also produces the broader distributions. So this, another thing that I can say regarding impact parameter space GPDs is that by simple definition of the form factor and the charge radius, we can compute this expectation value that will be algebraically related with the pion charge radius by this factor. This is a completely algebraic result. Good. So what about these distributions? Well, basically, as you may know, they sketch the likelihood of finding a parton with momentum fraction x at a certain transverse position B. Here I'm depicting a particular replica. Here we have the quark and the anti-quark, and we see that these are peaked near x going to 1. And remember, this is at the hadronic scale, so all the momentum is contained within the valence quarks. But when I evolve, let's say 2 GeV, we start to disentangle the momentum, and the fully dressed valence quarks lose identity. That means we generate C and gluon content. As a consequence, these peaks broaden and the maximum drifts. So they contribute less to the total momentum, so the distributions become, let's say, shorter and broader. So this was supposed to be an animation, but I sent the PDF, so sorry about that. So now, the final thing I would like to share concerning this exploration is that I can also compute the charge and mass distribution from the moments of the impact parameter space GPD. The charge is in blue in both cases. This is ASB, MF, and the mass is in yellow. So lattice case is in gray. So once again, we are seeing that the charge effect span over a larger domain than the mass effects. And it will be very interesting to see, for instance, whether or not this pattern holds in the case of the proton, and what happens, for instance, with this ratio in the case of the proton. Hopefully we will have something in the time coming. So, conclusions and scope. So I started with a question, from the empirical knowledge of form factors and PDFs, can we get the GPD, the pion GPD? Well, my partial answer is the following: yes, I can do that with some premises. First, I'm writing down the GPD from a overlap representation for like from wave functions, and I want those like from wave functions to be factorized, such that I can have this very nice expression here. From the experiment or lattice, I have the PDF defined at some scale that it is for sure not the hadronic scale. By definition, it needs not to be the hadronic scale. So I need to evolve it down to the hadronic scale, and I will use the all orders evolution I introduced during this talk. And finally, appealing to the sum rule, I generate this last piece of the GPD. So yes, I can do that, but I am limited to the glab region. Nonetheless, in this region, I can compute the charge, mass, and spatial distributions already. I can extend it to the ERVL domain if needed, and I can evolve back to experimentally or lattice relevant scales. Here is the scale of 2 GeV for the valence, the C, and the gluon, for example. And something that I would like to highlight is that the preliminary computation from the Schwinger equations of the gravitational form factors are in agreement with the data-driven exploration. So hopefully we will get this soon, at least on the archive. So good. What else is to be done? We can perform an analogous study for the kaon, even though the information of the empirical information of the kaon is scarce. Actually, we only have this ratio U chi, U pi. We don't have the individual PDF. And well, from doing this exercise using this ratio, I get this band over here and this pion and kaon distributions. But this is just very preliminary. To build up the GPD, I need the information on the electromagnetic form factor, but basically for the kaon, I just have the charge radius. So let's see what happens in the future. And finally, because I have a collection of different curves for the electromagnetic form factor, and this collection of curves have been validated by an external, completely independent observable, namely the PDF, I can trust in this collection of curves, in this ensemble of curves. So I can use them elsewhere. And for instance, this is the case of the pion box contribution to the muon's anomalous magnetic moment. I can plug in my form factors in this master integral and get some number that it is not only driven by the form factor, but also the PDF. This has an external validation. And that will be all. Thank you so much.
One sec.
Thank you for the very nice talk. Do you hear me? It was really interesting. I have a question. If you go back two slides where you show the factorized picture, another one here. So the question is a bit naive, but what do you really learn from that? Because the pion GPD has been studied in many models for the pion for years, right?
Mm-hmm.
And what you can see is that even the simplest contact interaction brings you a non-factorizable expression. In some limited data, it is factorizable, right? But I would think that the dynamics inside a pion could imply some non-factorizable effect or not. So don't you lose some kind of information of the dynamics by doing that?
Well, two things. One, I have seen a couple of times, and I just show you some exercise here, that if a Bethe-Salpeter wave function can be parameterized in terms of perturbation theory integral representation, I always get the kind of correlations that are proportional to the mass of the meson and to the difference between the quark and anti-quark masses. I always get that. So I'm telling you, because the pion mass is so low, and because the pion, the flavor asymmetry is so low between the D and U quarks, it might be sensible. Furthermore, I am not computing, for instance, TMDs. I am computing integrated quantities. So I expect that even the non-factorized part that remains is wiped out after the integration. I will worry about the TMDs, but I will not worry about GPDs or PDFs because they are integrated quantities.
And just one comment. The data, what you call data for the PDFs, they are not the data. I think it was a request by Wally Melnichuk many years ago, and it would be great if people could stop calling them data. They are not data. They are cooked data, cooked extraction of the data.
Yeah.
So it is not data. You have to be careful with what you use. And I think
I call them at some point different interpretations. Yes. Of course.
We have a question over there.
Yeah. Is this factorized ansatz compatible with the expectation that there will be different poles in the electromagnetic and gravitational form factors?
Actually, as far as I understand, you mean the time-like poles, right?
Yes.
This escapes the domain of the GPD. This only can be seen, I guess, from GTAs or something like that. So I don't see them. I don't see them.
Mellon moments of the GPD should give form factors, and the form factors do have time-like poles in them. The gravitational and electromagnetic form factors will have different poles.
Yeah, I know if from a diagrammatical point of view, I need to see the poles. But in this case, I am limited to space-like form factors, and I know nothing about the interaction with either the electromagnetic or the gravitational proof.
Any more questions, comments? Yes.
It's more curiosity.
Yeah.
Well, I think this factorization of the valence wave function is very, very useful. Can you pin down to some particular properties of your kernel of the bits of Pete equation that the factorization is because I know in general that when you go to very large momentum transfer, it factorizes. But I'm surprised that it works very well in the infrared region, even for low momentum. So I'm guessing that is some consequence of the interacting kernel that you use. I don't know if you have thought on that, because I think it's a very useful property.
Oh, I have never thought about the interaction, but just what I said before, I have seen that if I project out my numerical solutions into an Nakanishi representation, I always get this kind of X and K perp correlations, so which are driven by the mass of the pion, and so almost factorized.
Because, I mean, the Nakanishi weight function, this is a little technical. You use only depending on the compact variable, I think, or the non-compact. Normally it has two depending.
Yeah,
the compact and the non-compact. And I think you use only one of them.
On the first example, I use one of them. On the second example, I use a particular one that, let me try to put it here. This is example one. One of the variables have been integrated out, and then I get this mass scale in the denominator. The variable that goes from that integrates to infinity has been integrated out, so I get just this, just one variable. In the second case, that one, I use the one with two variables, but after integrating one variable, I get, instead of a mass scale, I get this combination of this function, not a mass scale, but this function. So I go back to having only one variable. So this is a very particular convenient case.
Just one comment on the experimental pion form factor, which several people have talked about. Extracting a form factor for a particle like the pion at high Q squared is not unambiguous. It's very difficult to extract a form factor for a virtual particle and preserve gauge invariance, because there are actually many form factors in the problem.
Yeah.
The exact extent of the uncertainty in the pion form factor it's not clear. I had a student, Robert Perry, who looked at some ways of preserving gauge invariance while having realistic form factors. I just suggest people might look at that, but there wasn't a rigorous answer.
Interesting.
You have a question?
I think I have. So going back to your GPTs, so they are not continuous functions. They are continuous at x equals psi?
I don't have the plot, but yes.
They are continuous.
Yes, but yeah.
Because we see something different in the lattice.
Yes, I mean, I can only compute this in the graph domain, so anything that escapes this domain is beyond the overlap.
There's always also another comment. You use many times, I think, lattice data as a benchmark, including average X of the pion, I think.
Excuse me?
You use many times, you use lattice data as a benchmark, including the average X of the pion, right?
Yes.
So I don't know which data exactly you used. I want to just a comment. As far as I know, there's only really one completely consistent calculation of that, because most of the calculations, they just disregard the disconnected contributions.
Oh.
So as far as I know, there is only one that includes everything and do the decomposition and gives you the average X.
Okay. So yes, I am using the moments from these 3 different collaborations, but I only keeping those that satisfy the recurrence relation I show you. So I have that I will get asymmetric PDF at the hadronic scale, and also I am discharging those moments that don't fall within the physical bounds. So these are the moments that I am keeping, and from these 3 different collaborations.
Okay. I may be the number 3 there, but I don't know that.
Okay.
More questions, comments? I have a question for you. In some point, you mentioned that there is a cancellation between among the effective charge that you are employing. And do you understand why this dependency is washed out?
Yes, actually.
And then you don't have any dependence on the alpha anymore?
I am writing down in a very convenient way this alpha, such that this function here contains the information that tells you about the saturation and the vanishing of the London pole. And I don't have the details, but if you work out the math of this particular parenthesis here, you arrive at this ratio.
But then your alpha does not have a dependence on Q. You just put the dependence of the running mass, basically.
This has a dependence on Q here.
But then
on the scale.
The expression that you just showed, the dependency is M.
No, not running mass. I am calling this function capital M, but this is not running mass. This is some profile function that interpolates this infrared and ultraviolet domains.
Not the running mass.
No.
Okay. If you don't have any, do you have questions, Bruno?
Yep. This is. This coupling is the same coupling I showed you at the beginning, the process-independent effective coupling. And in the interpolation between the infrared and ultraviolet domain that comes encoded here, I get to choose my value of lambda QCD. And when I choose my value of lambda QCD is basically choosing the scheme I want to use. I am choosing the perturbative tail I want.
Any more questions, comments? If not, let's thank Kepani for the nice talk. Now you have a break, and you come back at 4:10, right? Bruno, do you have any announcement? No. So session is Aurora Courtois. She's going to talk about phenomenology of PDFs and the uncertainty determination of proton and pion PDFs.
Thank you so much for inviting me. So it's the second workshop of the 2 weeks. So there was another one last week here and 3 kilometers away. And I promise it's not the same talk exactly. I will repeat a few things, but not exactly the same. Okay. So we heard about pion PDFs from Schwinger Dyson and other kind of extractions. We heard about global analysis as well, and I will try to make a broader picture. It's only about phenomenology, so I won't talk about. But that's already a big program, right? So I won't talk about Schwinger Dyson. I won't talk about other things. I will talk about how we can extract reliable and faithful PDFs from data. And the data, okay. And I will talk about that, okay? So this is all the funding agencies that we need to acknowledge. And Bruno for paying us too. Thank you, Bruno. And Pacheco as well for the last week. Okay, so I mixed 2 titles. So when I call reliable and faithful uncertainty, the new term, it's an old term, the term that is used, and it comes from this rising machine learning area, it's epistemic uncertainties. So it's towards epistemic pattern distributions, and it's work done plus work in progress plus work almost finished plus blah, blah, blah. On 2 groups, the overlapping groups. So it's with the CTEC-T collaboration. So we have this paper that I like very much about pattern distributions need representative sampling. And forthcoming studies in the framework of proton PDFs. In that case, proton PDFs are much more well-known than pion PDF, and I will explain why in a few minutes. And the new, the almost done, the upcoming, it's almost finished. I will show you the preliminary results. Still not the last ones. It's a Phantomas, and I will explain why Phantomas. It's the Phantomas team, which is an overlap of XFeater and CTEC-T plus students working on that. Phantomas is a full framework that we designed to evolve towards epistemic uncertainties. And we are extracting the pion PDF using that new framework. Okay, let me talk about that. Okay, since it's poetic is about the EIC, we need to connect to the EIC physics, which we are really happy to do, of course. And I took that piece from the webpage of the EIC and the beautiful picture as well. And so we have a list of promise that somehow we all did to the funding agencies and also to ourselves, that we will try to extract and to find answers to those questions, or try to have this quest for understanding of hadron structure. And so let's take those as hypothesis testing. So how are we going to test that? And how are we going to make sure that we have hints, we have more than hints, we have proofs, we have evidence for specific observables and specific claims. So if you think about testing of hypotheses, we need to understand how we test. So the one I highlighted here, the one that I underlined, depends on and heavily relies on PDFs, either unpolarized or polarized or not. But we need to understand the uncertainty of PDFs to make sure that the question we want to answer actually can be answered as evidence or hints to high significance in the IC. So we still have some time to do that, but it applies to the IC, but it's actually right now it's in testing at the LHC, for example. Okay, so 3 weeks ago we had DIS at Michigan State University. It was not so long ago. And we had 2 keynote speakers at the end of the conference. One was Daniel de Florian, which is EIC supporter from Latin America as well. So it's good to support more Latinos. What he did is he really highlighted the need for precision. So up to now, we have next to leading on our PDFs, and we are moving towards next 3LO QCD evaluations and PDFs as well. So there's a need for precision to either look for new physics or other things. So it's really important. At the same time, and that came with this all of a sudden interest for the W mass, there's a Martin Bonnekamp who highlighted the need for accuracy. And what he did in his keynote talk, he talked about the working group 1 in which we had a session about uncertainty quantification and how important it is to understand the uncertainties when we need to make claim about either standard model or new physics or try to understand hadronic physics and low energy QCD, for example. And so those are the things that are important. And here I will talk more about accuracy than about precision, but both should be addressed. Okay, so we heard about the shape of PDFs, but the shape of PDF, of course, will teach us a lot of things about non-perturbative QCD, even though people at LHE don't really care about that, but we do care about the shape of PDFs as a first principle way to access first principle information. So it's PDFs are non-perturbative, it's low energy QCD, and how do we do that? So this shape in X is not known from PQCD, and it is extracted, it is learned from the experimental data, the data, right? That are sensitive to some PDF, say combinations or other things. And what you can do to extract them first, people are trying to have some hints of behavior at low scales, but you don't necessarily need that. You can have this as a guideline. And then you make predictions for other processes. And that's how it works, right? And that's extremely important. So things we know, we have classes of first principles that constrain the X dependence on PDFs. There's the positivity of cross-sections. It has been a long debate. It is still something that is debated right now about positivity of the unpolarized PDFs or the polarized PDFs and so on, because it is not as obvious as it seems. The support in X, it's 0 to 1. This is something that is well known from the model point of view. The endpoint, as we heard before, is for the pion the tricky part. What is the behavior of the endpoint? We know it should go to 0, but we don't exactly know how. And then we have the sum rules. That is valid for some of the PDFs. Not all PDFs have sum rules, but this is those are the classes that we have. And then we can have also other early QCD-based guesses about PDFs, but that's about how we know. Okay. Then we heard during this workshop and the one before that, of course, you can evaluate in QFT in the model, and you have to make sure that you have the symmetries you need. But then you rely on the hadronic wave function, and that's not trivial to define. And it is model-based and all those things, right? But those two approaches are important. So once you extract the PDFs from the data, so global analysis, we rely on that part. We don't take into account what happens in models, okay? Then you need to assess an uncertainty to your PDF, and that's actually the gist of the game, right? You need to understand how to do that, and that's what I will agree now is the most important thing to have to do right now, right? Okay, so you need the uncertainty. It's an advanced problem. We have a multivariate problem of statistics here, and right now it is extremely evolving due to the fact that we have a lot of data. We go to big data, big spaces of parameters, and we have AI/ML, which is intelligent intelligence and machine learning, which is the hot topic, the trending topic of the moment. And the reason is that it's extremely interesting and it's helpful, but we need to understand how to use it well. Okay. And so once you understand the uncertainty, you really try to refine. And we got to the point in which we decided that it was interesting to have these two kind of uncertainties, which is epistemic against aleatory uncertainties. The aleatory one, they are the statistical uncertainties that are reducible from the feed point of view. Perhaps you can increase, of course, improve your experiments, but once you have a data set, you can't change that. And then you have the epistemic that basically reflects the lack of knowledge of some things, all the things. It can be reduced, but not always. And it's what we can call the bias, if you like. And I will talk mainly about this one. Okay, so how do we do analysis, global analysis of fits of the data, if you like? There are mainly two approach and hybrid versions of each approach. Is that you will minimize your objective function, and you can have this HR methodology. Or you can have the Monte Carlo methodology where you have replicas and then you minimize and you have like 200, 100,000 replicas. And here you can, in your n-dimensional space of parameter, you find the parabola and you define the minimum. And so since we talk about really high dimensional space, it's a multivariate analysis. And in those analyses, you would have sampling that occurs at many, many stages. It can happen at parameter space, bootstrap, priors, statistical analysis, objective functions. You have to sample over many, many things. And this is something that we also have in common with lattice practitioners, that sampling or inverse problem must happen a lot of time. And especially for PDF analysis, we talk about more than, in case of the Hessian, more than 20 dimensions. And if you talk about Monte Carlo, depending on how you do that, neural network is much, much higher in space. Sampling becomes extremely complex in high dimension. Okay, so how do we account for these epistemic uncertainties? So I have a bias for CTEC, as you can imagine. So in the CT18 analysis, if you compare the blue band, which is the uncertainty, is the ratio of the central to the uncertainty. For the blue band is the uncertainty, and then you can see all the green curves represent alternative parameterization that, as it turns out, are contained inside the uncertainty. It means that if you change your functional form for the PDF, this function of x that you try to define, which is the truth, you will see that it is not determined well when there's no data. And actually, by changing the functional form, you will end up in the uncertainty that was defined by the group. This uncertainty comes for minimizing this chi-square and the parabola, and also the way you define it depends on the tolerance criteria as well. In the case of the Monte Carlo base, that's what you have for an NPDF, for example. We had this paper about the hopscotch, we call it the hopscotch, and in which we classified and we found the effective dimensions of the space based on some cross sections to actually account for this bias due to lack of knowledge, these epistemic uncertainties, and extended the possible solutions found by an NPDF, for example. So that's what the nominal solution here, and we propose that you can find solutions with lower chi-square if you use this technique of the hopscotch. And of course, it increases the uncertainty, right? Okay, since we talk about hypothesis testing, we want to test a few things, and we can give examples if you like. So how does it depend on what we have? So it will depend on the data, sensitivity of the data. So also the X and Q square coverage, so it's always good to increase it. Have data that are sensitive to different flavor combinations or ratios or things like that. Quality of the data, and then the uncertainties found in the PDFs, in the fits, right? And so that's the diagram we have now. That's for my colleague Pavel Danowski, and that's the future that we want to explore. We started to explore in the CT group. So we really want to have a way to sample in a representative way, test of PDFs outside the fit, inside the fit, and acceptable functions. We want to test all those things to get to epistemic PDF uncertainty that will allow us to have precision PDF applications and reliable applications. Okay, so where does that all come from? Well, basically, what are the criteria to understand PDFs? So every given number of years, it's been a second time only, the three main groups, CT, MSHT, and an NPDF, go together and propose a set. There's a benchmark exercise and then a set proposed for the LHC. So it's called PDF for LHC, and last year we released PDF for LHC 21. And there's a benchmarking exercise, and then a combination of the sets. And so during this exercise, you actually learn about the difference between the groups. You try to converge into a few things. And what you can see here is that you have different uncertainties. So you would have added PDF 4.0 here, MSHT 20 here, CT is the red ellipse, and PDF for LHC is the brown one somewhere here around. And you can see that that's what we find. We have the combined PDF, the uncertainties, that's what we get. But during the benchmarking exercise, what we found is that for in many, many cases, there is a systematic, even if when you benchmark, you take the same set of data, same set of parameters, and you will try to minimize the difference in the technique. The only difference comes from methodology. And what we found is that systematically, the neural network, the Monte Carlo analysis, would have a smaller uncertainty than the Hessian ones. And the question is, where does it come from? And that's what we studied. And our answer to that was that it comes from the sampling uncertainty, the bias of uncertainty. And so we studied the role of this sampling bias. And actually, we are not alone. I don't know if it's written somewhere. Yeah, we are not alone. This idea of sampling bias comes from statistical analysis, in which people started to analyze, for example, the vaccine uptake in the USD elections. I think it was when Trump was elected. Understand why the surveys would not reflect exactly what was obtained after that. It's because of the sampling, the quality of the data, and how it is done. So there are a few papers that go into this idea about the quality of the sampling, the big data paradox. The more data you have, the less certain you get about the results. This big data paradox is also used in clinical practice, and also other papers that show that effective dimensions, high effective dimension in problem should lead to higher uncertainty. And that's what we found here too, right? And so there's a whole framework coming from this called the trio identity that is used to parameterize this sampling bias. So using that, we've defined two classes, and that's what I've said a bit before, of uncertainty. So you would have, before you already have theoretical, experimental, methodology, and parameterization, and all those four categories of uncertainties actually can be also parallel into what we call the PDF fitting accuracy, which corresponds to, say, each fit, say, the central value, for example. There's a goodness of fit criteria for each central value with the best fit, if you like. And then when you take the ensemble of PDFs, which means you have the full set that accounts, reflects the uncertainty, this set, this PDF ensemble, also the way you choose this ensemble actually will suffer, if you like, or we need to take into account the sampling accuracy as well. And that's what I'm talking about. So it's something on top of what you usually have for each goodness of fit. You also have to make sure that this ensemble of PDFs that you show and you decide to get actually is reliable. Okay, so where does it come from? So I took this from this picture from these clinical studies from this person. And so that's a bit of a cartoon. Okay, let me see if I can try to explain that. So say you have a truth in blue, okay? And then you have a model of the truth. This model of the truth, in that case, is not so close, okay? It is somewhere here. And then if you have a small sample, if you have a small dimensional space, you would expect actually to have an uncertainty that they call here the confidence interval that is not so small, right? And then the usual expectation is that when you increase the number of n, the sample, the size of the sample, then you have this law of large numbers that tells you that you have to decrease the uncertainty will decrease as 1 over square root of n, right? And so in that case, what you would have a shrunk confidence interval here that, as it turns out, is actually really far from the truth in that example, right? And so the question is, why does this, in this example, this large n limit, this law of large numbers, prevents us from including the truth? What prevents us from including the truth is the reducible uncertainty, is the quality of the sample, is how you sample the BF. So you can't reduce this red uncertainty here, but what you can reduce is actually the way you sample. You can try to understand, or you can at least include the sampling bias in your uncertainty, so you include the truth, or you can try to reduce it. And that's what we want to talk about. And this idea of sampling bias comes from Xiaoli Meng. It was published a few years ago, and it's really interesting. And so we propose an algorithm in which we take the Monte Carlo replicas, in that case of an NPDF. We try to reproduce the shape of their parabola in the Hessian space, and we actually in the hopscotch you have to jump, you throw this token and you go into this large effective dimensions, And in that way, you actually find solutions with a better chi-square. And so what we found here is that, so we compare, in that case, you would have CT18 and CT18Z. The two together make the most complete uncertainty coming from the CT18 analysis. And if you compare with NNPDF 4.0, you see that there's a difference of size. And once we include the new solutions that we found with this hopscotch mechanism, algorithm, if you like, we increase the uncertainty coming from Monte Carlo as well. And this, actually, this ellipse here corresponds to the plot more or less, well, in part to this gluon that I've shown before, that actually accounts for the sampling of parameter space in the case of the Hessian parameterizations, and here for the space of neural network analysis. And so we are not confident that in that case, the sampling accuracy is taken into account, and the new solutions we found for the hopscotch are much more inclusive of this problem. So why do I talk about that? It's just to say that we want to find the true PDF, we want to find this true central value, but we can have many solutions. It's not a unique solution, it's an inverse problem with uncertainties coming from different sources. And here we heard, and we will still hear about trying to understand dynamics of QCD, and that's an extremely interesting problem. And to do that, we study PDFs, okay? So this is something that you all know about. And of course, you have different scales. So if you take non-perturbative models, you would have a mu naught, like Kepanin talked about in his talk, and in which you would have some degrees of freedom that are not the same as the MS bar degrees of freedom that you would have in factorization theorem at higher energies. So there's a difference between the two, and you want to extract those PDFs from the data, and that's not exactly what corresponds to the non-perturbative point of view. And also, what you see the difference is that when you go to an increasing center of mass collisions, you would have, that's a low energy picture in which you have more like bound states and compact, that's the thing you want to understand. And you also want to understand the rest, but here you have PQCD, and then you have this leading order, this tree level diagram here. And if you increase the center of mass, you would have more and more corrections. So you have corrections here, like target mass corrections. You would have other corrections of a higher twist, and then you would have things that we don't know yet, we want to learn about. At higher energy, you have hadronic activity, like multi-parton scattering and all those things. So at any scale, we have different problems, and we want to connect the two or three pictures, the PQCD to the non-perturbative QCD, and try to learn about the true PDF, which is like a huge program. Okay, so the difference between what I will call non-perturbative PDFs, they're all non-perturbative, but that's the only way I found to call them, and the Pheno PDF is that non-perturbative PDFs are defined at a hadronic scale, which is much, much smaller than the factorization scale. And the Pheno PDFs are extracted when factorization is already valid, right? And so at low energy, you have, it's a pre-factorization picture, you have non-perturbative degrees of freedom, and it reflects the non-perturbative dynamics, which is the one we want to understand, right? And also at high energy, you have MS bar scheme, you have leading power approximation to fluid dynamics, and so on. Okay, just to give you an idea, that was for the pion, since we heard more about the pion. So in the model, you want to evaluate your PDF. You can extract, so you can have your bit separator amplitude if you like, and you can put it somewhere here, and you can evaluate in the model your PDF, and you get a result with your degrees of freedom in your model. While what you would do in global analysis, you would have the process, you would have the description in PQCD, and the unknown would be the PDF in this factorization picture, and you try to extract it. And those two pictures are not exactly the same. So now the question is, how do we try to combine the two, to bridge the two? So that's a real question. And sometimes we want to test, we want to test hypotheses here to understand from here to there, and the other way around. So for example, we want to test some local true or false statement. So do we see this behavior in X? Do we see this at that point? Or you want to test for functional behavior constraints. And this functional behavior is a famous 1 - X to the power beta fall off of the PDF, for example, that I'm going to talk about now. And there's a reference here if you want to check. Okay, and the same thing for the pion, but the pion is also interesting and you want to understand. And it's trickier to get from data because it's a pseudo-Gaussian boson, it's really light and it's not stable, so that's a bit more tricky. The good thing is that there's much more, okay, thank you. There's much more field theoretical approaches to that than for the proton, for example. Okay, so we want to test hypotheses. There's a long list of things we want to test. Lately, we heard about pretty charm, strange asymmetry, and things like that. So we want to test if there's a proof, if there's a hint or evidence of this thing in PDFs. That will be like a local in X true or false statement. It doesn't have to be local, but that's how people have done that so far. Or you want to test this functional behavior, this famous 1 minus x to the power beta. So what you want to do first, you need to check the compatibility of the data requiring from your analysis. You have to relax this constraint from your analysis, and you have to check if this behavior is still there once you relax in your analysis. And in the case of the functional behavior, this is not enough because it's much more complex. You need to account for what we call polynomial mimicry. A mimicry means that there's more than, so a polynomial of a given order can be mimicked by a polynomial of another order as well. Okay, and so that's why we want to explore the quark counting rules, which is the one giving you this beta here. That's an early QCD prediction that was followed by many groups. It has been argued that it's still be there. It's still be interesting, and I'm going to show a few things about that. Okay, and we want to explore this functional mimicry here, which is extremely interesting. Okay, so what does the quark counting rule tells you? It tells you that I'm just showing here the valence. There are also the rules for the C and for the gluon. So for the proton, it tells you that the PDF should fall off when x goes to 1. Then we need to define x goes to 1 as well. 1 minus x to the power 3. And for the pion, it should be 1 minus x to the power 2. All right? And so in that case, we want to check what happens, and we want to check as a if and only if condition, of course. So what you can first check is that your model agrees with the data, whatever you want to call data, or with analysis, if you like. And that's a necessary condition, but it's not sufficient, right? And so we want to check the evidence for this form, that this form is the one that is followed by nature in the data. It's much more complex. So let's first talk about this one. You can define this, effective exponent. So in the CT, this beta is A2, not beta. So you would have B2 here. And that's for the proton. So you check that you have 1 minus x to the power 3. And what you can check for the structure function, not the PDF, the structure function is that using the CT18 analysis, you can find that it agrees within uncertainties with this power of 3. As you can see here. What you can also see is that there are two types of uncertainties, and but you don't distinguish them really well. And some come from the parameterization as well. So in that case, there's one coming from the whole fit, another one coming from using 363 parameterization for the PDF analysis. And you can see it increases at large X because there's no much data at large X for the proton. And also when you go to small Q values, then you hit the resonance region. You cannot go in that region with a PDF, factorized PDF picture, for example. But that's so far so good, it seems to work. Okay, now you want to test this X shape. We have polynomial mimicry. And basically, for that, you can use the Bernstein polynomial or the Bezier curve, if you like. So the Bezier curves are polynomial on the Bernstein basis, and the CL are the coefficient of that polynomial, and the basis is just here. So Bezier curve has been used in design, for example. They were used to design the cars. That's how we call the phantom mass that you will understand in a few minutes when I show the plots. And you can actually modulate that, use Bezier curve to interpolate really well functions. And those Bezier curve, yes, they can be used for interpolation, and they're extremely helpful. If you can show that you can have a Bezier curve of degree 2 that is equivalent to one of degree 3, and so on and so forth. So in that case, this power 2 or 3 doesn't make much sense for the Bezier curve because they can be mimicked, right? You can have different ones. And so how can we use Bezier curve for global analysis? So the first thing is about interpolation, and then I will tell you how we use to fit. So we can test, in that case, the 1 minus x behavior, and if we have a well-defined function, a simple function, you define what you call control points. So those control points, when you pull on the position of the control points, you will change the curve. That's how it's used to make designs. You will change the curve, and you can reproduce this monomial in 1 minus x because you check this behavior, and you can really reconstruct, interpolate this curve without any problem. And if you take a more realistic function, it's much more complex, it would seem that you would have 1 minus x to the power 2, but you have all this complex polynomial here, and you want to reconstruct that, but then you take different points, take 9 points and try to reconstruct. This reconstruction will depend on where the control points are positioned. And what you can see is that you cannot meaningfully reconstruct this polynomial, and you cannot actually determine this 1 minus x to the power beta effective meaningfully without having a good handle on the really at x goes to 1. So it means that you cannot actually determine this 1 minus x to the power 3 or 2 for the pion uniquely. You really need to have more data, and so far it's impossible to find it. Okay, and so why do I talk about that? Because you've heard before in previous talks that the large X behavior of the pion is a debate. It's been a debate. Hopefully it will stop soon. So I'm showing those points that are not data points, okay? Those are the extracted points from E615. And I'm showing this famous 1 minus x to the power 2 that is expected if you would believe that you can check that. But of course, you have here a different problem is that, well, there is polynomial mimicry, and also you have this emergence of hadronic mass that broadens the PDF of Q naught. So at some point, you would have this concurring effect coming from the broadening of the PDF from emergence of mass, and this possible 1 minus x to the power 2. And of course, you cannot distinguish the two in your analysis, also due to polynomial mimicry. And also due to mimicry, you would have a change of degrees of freedom that will be expressed as different powers of 1 minus x, because you don't have ms bar quarks, you don't expect to have this behavior at all. And so I think that there shouldn't be any debate here, because we cannot just disentangle the two effects, and also anything based on this polynomial mimicry. And we had a lot of discussion last week, and I think we will have some this week as well about that. Okay, and about the large X behavior, this A2 effective of B effective. There was an analysis by JAM. They've done a few fits of the pion PDF, and also they tried to have large X summation. And what they find is that some agree with 2, some with 1, but it seems that the most accepted in the community is the double Mellin, and so they find that too. And also, and there's this paper in the lattice partitioner that discussed all the issue about the inverse problem and how it is difficult to actually find this power beta, all those things. So this discussion in this paper is similar to what we have shown in our paper as well. And so what we can see is that it's all the degrees within uncertainties that reflect this polynomial mimicry, the change of degrees of freedom, and all those things. Okay, the second way we can use Bezier curves for global analysis is what I call the Fantomas for QCD. So this is the car of Fantomas. It was designed, it's a Citroën DS. It was designed by Bezier curves, and that's how we connected the two things. And so as you can see, the car flies from UNAM to SMU, that's Dallas, Southern Place University, and then it flies back and forth, of course, right? So it's a collaboration that's funded by CONACYT and also by this INNN of QCD challenges. And that's a picture of the team. So those are the students, Max, Lucas, that's Pavel, that's Fred, and that's me here. And we were at Fermilab, we took the picture. And actually what we do in this team of Fantomas, we use Bezier curve to actually generate more functional forms to actually try to systematically increase the number of permutations we have, so we can have this kind of 363 or more different permutations for the PDFs to try to have an alternative to neural networks still using the Hessian methodology. So how does it work? So this is just fake data. We just, we took a distribution and wanted to fit it, and that's it, right? So it's kind of made up, right? So we had a true distribution. The truth is the red one. And from that, we generate with some noise some data just to illustrate how it works, okay? This is not anything, this is not any real data, okay? So we have this function here. And when you have a classical fit, with opposed to the metamorph is what we use in phantom as metamorph fit. So in the classical fit, you would have what you call the carrier function with the parameters, and you could have a Bézier curve. So CT18 also uses the Bézier curve. The difference with the metamorph fit here is that instead of fitting the parameters that will come here, the coefficient of the expansion, we actually fit the shift of the control point. So we choose control points, and I'll show them. Okay. So you choose control points here, and the way you actually, what you actually determine in that case is not the coefficient, is how the control points are pulled to form the curve. So in the case of the Bézier curve, you can pull on the strings and change the control points, and you would have a different curve. So what we parameterize is how, when you minimize, when you want to get a curve close to your points, you will minimize some objective function, and you parameterize here the pulls on those control points. And that's why you can see here that we're able to reproduce here. So that's the main difference with the classical fit. And here we can change the degree of the polynomial. We can choose 0, 1, 2, 3, 4, 5. Okay, thank you. As much as you want without overfitting. Of course, you need to control it well. And also, we allow the carrier function to vary. So that's the usual x to the power alpha and x to the power beta. Okay, and then you can do that in various ways. You can generate it on the fly, and then you have a good sampling of parameter space in that case. Let me show you a few results. So, and then we put this routine, so this version is put on XFitter framework, and XFitter already had a fit for the pion, so we took the opportunity to redo the pion fit ourselves. But what we did, so that those are the data from Drelian that XFitter includes, and we added a few points from the leading neutron. It's a tag neutron, basically, that we heard about this morning, but this one goes in the pion here. And so we added that to constrain a few things. So first, we tried to redo the XFitter analysis, and what we realized is that with only Drelian data, which is large X, very large X, as you can see, you don't have a good handle on the C and gluon. So it's next to leading order in that case. I think I put it somewhere. It's next to leading order, okay? And without leading neutron, you don't have a good handle on separation between C and gluon, and you end up with a huge uncertainty. And that's also what JAM finds. And it's, just a note here, it actually justifies how we need more processes and more data from EIC and Jefferson Lab 22 perhaps to do that. Okay, and so you want to study the momentum fractions coming from those PDFs, and you can see that the valence is pretty well constrained, more or less, but the C and the gluon are all over the place. They are completely unconstrained from only this data. So we added a few, only 29 points from the sliding neutron, and what you can see is that this is for a selection of NM and control points. This is not exhaustive. We want to do more fits, include more of those before we propose the final uncertainty band. But basically what you would have, so I put the central values and the combined uncertainty in gray. Okay, that's what you would see. And so we can see that the valence PDF is pretty well determined at large X. It falls very much like 1 message to the power 1. It doesn't fall like 1 message to the power 2. And it is very similar to what a JAM and XFitter gets at large X. Okay, and so then you go to the gluon is much more determined in that case than before, and you can see it raises really, really well. Just using a few leading neutron data already help getting a much better, much narrower uncertainty. And as you can see here, it is narrow, but it is inclusive of the lack of knowledge we have. And there are still a few replicas that have this funny behavior, and they have a good chi-square. It is totally allowed and accepted. So the band I show you here is 68%. If you increase to 90%, you would have much more of those replicas included here too. Okay, and then same for the C, and you can see the C as this uncertainty showing up. Okay, so there's not much data constraint here, about 0.5 here too. It is less entangled than before. So also what we want to understand is the momentum fraction. You can see that adding leading neutron slightly narrows down the distributions, but not so much. So there is a difference, but not so much. I don't put the numbers here, but basically the uncertainty is still pretty large, but it's compatible with the other groups with a larger uncertainty. And we feel we are inclusive of the lack of knowledge at small x and or around x equal 0.1 where you don't have so much data actually. And we really have this good sampling of the parameter space. So if you want to compare with the analysis, it would be basically JAM21 and XFeeder. As I said, this is preliminary because we have not finished our span of, well, we never finished the span, but you want to make sure that you actually inclusive of the most representative data parameters that you would like. And so we want to explore it a bit more. What you see now is that the valence is pretty similar to what the other groups find. We have a larger uncertainty at the valence region. The gluon blows a bit more up at larger values, and the C seems to be compatible with what JAM finds. So actually, XFeeder does not include leading neutrons. That's why there's a larger uncertainty, and we are pretty much compatible now. We want to finish exploring more all the possibilities that this metamorph allow us to do. Okay, so a few things just to compare this Dralian against Dralian plus leading neutron. So we want first to compare the methodologies. So in our case, we don't use any bootstrapping. We just parameterize we have the parameter space coming from this metamorph, this basic curve parameterization and nothing else. And so we want to compare with what happened in the case of JAM, for example, that uses bootstrap and this iterative Monte Carlo, okay, which is different. We are trying to compare with them. So when you can see when they add leading neutron, they also shrink the uncertainty very much at small x. And in the case, there's also, we've found that there is some dependence where there's not so much data in the choice of the procedure we use to as the Hessian matrix. In the XFeeder framework, we have to understand that, and we have to make sure that we are inclusive of all this. And it should be finished soon. We have to run a few more fits and test, understand this, and write the paper. But basically, that's what we have. Okay, so I go to my conclusions. So I hope I convinced you that there are many sources of uncertainties, and we have extended the usual framework to epistemic. That includes sampling accuracy. Okay, we really want to go into this epistemic PDFs, trying to have to build tests of PDFs and all those things after the fit. Try to understand how you can define and explore this large dimensions, effective dimensions. And based on those works we had, we also defined a framework to have an improved parameterization, more like a dynamical way to parameterize the PDFs using Bezier curves. That's the Fantomas framework, in which we use this metamorph that is embedded into the XFeeder framework. And we propose reliable uncertainty coming from the PDF analysis next to leading order for the pion, right? So it should be larger, but there's no constraint from the data, and we're seeing this effect, and we want to improve on that before we publish, okay? But it gives a really good hope. And just a final thing, the endpoint behavior, the pion distribution seems to follow more the trend given by mass generation. I'm sorry, but the quark counting rules. It is due to many effects that I explained, mimicry and all those things. The question also is how to quantify uncertainty in non-perturbative calculations. And also, that was from last week, and that's an open question. At what Q values will PQCD take over for the pion? And that's an open question because the pion doesn't seem to want to be too constrained by PQCD too early in Q. Okay, thank you.
Questions, comments? You have one?
I don't see anything. Oh, okay. I'm sorry. There's also a bay. Okay, I'm sorry.
Yeah, that was wonderful. I think I learned quite a few things. I have lots of detailed questions which we'll discuss.
Sure.
But generally, at a high level, how do you compare these new method that, at least for me, it was new, to the trend that I see from parameter-less PDF fitting that comes from the neural networks, et cetera, would you use, I mean, is it, what was your, I mean, my instinct is that if you go into regions of X and Q square where there's no data, I would rely on them. However, if you know something about it and then to improve things based on what we know, I think your method would work more reliably. Is that generally the idea, or how would you comment on that?
So the idea is complementary, right? So in that case, we don't rely on so much on the architecture and the choice you have to make when you have to build your architecture of neural network. So at some point when neural network build their analysis, they have to make some choice, and they should sample over hyperparameter space, for example, which is not something that is easy to do. So what we've shown before in the case of the hopscotch is that they might not be doing it systematically, or they might not average, and that's why we found other solutions that would have an improved chi-squared, and that's difficult to span because you have a large dimension. Large dimensional space. So in our case, this technique is to use the well-known Hessian methodology that is okay to be improved, but to try to have an improved parameterization in which you could systematically change. This is the first analysis we do, right? You can change the position of the control points, you could change the degree of the polynomial, and you can try to do it systematically and try to improve or try to find the best option to do it and to span as much as you can, still using the Hessian methodology. And you could have like more replicas, for example, without using the bootstrap. So here there's no bootstrap at all, for example, in our curve.
Yeah, but sorry, one last question. This method depends on the pull of the error bar.
But
so if you don't have data in that study, you don't have that. And that's why I was asking whether...
That's a good question. So, okay, so the ultimate idea is to use the data to pull the strings, and you are right. But so far we don't do that. We just choose the points. So let me just go back. And in that case, what I call data would be what I said not to call data, okay? So, okay, in that case you have data, but in a PDF analysis, you still can't pull on the data, right? So you choose the position of the control points. So far, that's what we do systematically, and we try to study what is the best position and how it changes. In the future, or when it's possible, in the case of the PDF, we have 1,000 of data, so it's difficult to pull the strings from that. It's perhaps trying to check how to use the data to do it, as you said. So far, we have not done that. So far, we just choose control points, depending on the degree of the polynomial we have, and we check how closer it goes. But yeah, at some point, it would be better to use real data to do that. I agree.
Yeah, thanks. In your perspective, how does this relate to the choice of tolerance in the Hessian uncertainty analysis? Because choosing higher value for the tolerance has been, at least some people have associated it with the parameterization bias. So does your new methodology give something new on this issue?
Okay, so actually, internally, we call this hopscotch paper, we call it the justification of the tolerance criteria, right? So when you think about this, so when we've done, so we can check that what we find for an NPDF, the size we find is more compatible with the size found by CT18, for example. So in that case, the tolerance for CT18 is about 36 at 1 sigma. And as you can see, when you span the parameter space, you have, in that case, 363 parameterization here, you will produce this tolerance, what you obtain with the tolerance. So this really high tolerance. And that's how this ellipse is obtained. And when we do separately the hopscotch on the NNPDF analysis, what we find is an area that is more or less compatible. So somehow this sampling accuracy, sampling bias justifies the use of the tolerance. I don't know if it was a question or not. I'm not sure.
Yeah, this was close to what I was asking. But maybe furthermore, now that you changed the way that you parameterize to maybe a more complete set of different parameterizations, how does this affect your choice of tolerance?
That's the next paper we have to write. So CT18 is moving into CT22X, and the next thing we're gonna do is use all those tools to quantify and justify better the tolerance. So that's something we're working on. Yes, that's on the list. Yes, it's a high priority thing. Yeah.
Very good. Nice.
Any more questions?
Here on this Tobias.
Tobias. Wait a second, Tobias.
So it's very naive. What I'm going to ask, I may be completely upside down. You mentioned the MS bar quark.
Yes.
So I don't know if this is the momentum fraction you are referring when you look to the PDF, or and how it is related to that image that the quarks are dressed. It seems that are different degrees of freedom. And can you give a naive answer?
But I think that they are not. That's what we have to understand, right? As far as I understand, they are not. Well, MS bar degrees of freedom do not reflect anything. Well, you have the normalization, of course, but you don't have any dynamics in there so far. It's pure PQCD, right? Yeah. Yeah, so factorization is done in PQCD, yes. There's nothing else than just PQCD when you do factorization. That's a question. I have no. That's a question for you. Well, there have been schemes. People have I don't know. Perhaps you know, Christina. There are some running of the mass. For example, if you have this the running mass, and if you go into the infrared, you would have. Some people have shown that there's a connection, but I don't know how well it is established. Perhaps do you have... If
he's connected with the perturbative behavior.
Yes.
Yes, you have the connection. If
so
you
there's
have
a connection.
If you have a current mass, you are going to have a perturbative behavior. If you don't, use another perturbative behavior. But always, at least in Schwinger Dyson equation, you are going to recover the correct perturbative behavior, and you know what it should be.
In the MS bar scheme?
In any scheme. You can change it from one scheme to the other. The scheme is not the problem.
Okay, so she has the answer.
Yeah, you can change it. Is the log or Powell law running?
I understand that this is basically fixed, but I was just wondering because the practitioner used this recipe, and it seems to me that X scheme maybe is something else.
What is X? I mean, Bjorken X?
Yeah, the Bjorken X. I understand.
Oh yeah. So it is different too. So what we call Bjorken X. What is not after leading order is not Bjorken X anymore, but you can define it as the way you define it is slightly different. And then on the Lycon, you would, depending on your model. So I guess on Lycon models, you will see they have X plus. Well, it will be K plus over P plus. I think it has to perhaps to do with what is a gluon. Is it a perturbative gluon or non-perturbative gluon? Or the things like that. Yeah.
There is a comment there. I don't know if it's about that.
Just as kind of a quick comment along that line of thought, at the very least in the NJL model, you have current quarks and you have dressed quarks, and if you're going to calculate something like a PDF or a GPD, you need to know how the current quarks are distributed inside of the dressed quarks if you're going to want to map this onto something to make empirical predictions with.
Well, you have the gap equation. This is what you mean? The gap equation, yeah, right? Yeah, but that's one over, there are hundreds of them, but I think that the lattice is at some model independent, if I can call it like this, continuation of the quark mass. Anyway. Well, yes, yes. That's model dependent still, yeah. Very.
More comments? If not, let's thank Aurora and all the speakers in the afternoon. Bruno, do you have announcement? The last announcement.
Okay, thank you first to all the speakers for such a nice first day after most of you had a long trip. I sent an email, but I don't have the students' email, so I told their advisors. So about the change I announced this morning, right? So we start at 9 o'clock, but all talks are shifted because of the first speaker is missing, and therefore we'll have the poster session. So the new program should be in your email. Another announcement, I spoke to the director of the ICTP, and because you all worked so nicely, I bribed him a little bit, and so we're going to have a dinner, probably on Thursday night, I'm not sure yet, in a churrascaria, and which will be paid for. No alcohol, sorry, that you have to pay yourself. But so we managed to get this today. So thank you very much, and if there are any other questions, ask me. Also thanks to my Brazilian colleagues who helped me, Tobias Federico here, João Pacheco de Melo, Kazuo Tsushima, Gustavo Crayon, and Aline Cristina Aguilar. Thank you very much, and see you tomorrow.